a problem of finding the shortest distance from a source vertex to everywhere else in the graph, right? Although our original intention was to find the shortest distance from a given vertex, we'll call the source vertex, to some other vertex in the graph. It turns out we can't help ourselves but solve a sort of seemingly larger problem of finding the shortest path from that source vertex to every other vertex in the graph. That's kind of a byproduct of solving the original problem. Okay, so let's write down this. So today, what we want to do is I want to start by writing down the procedure in pseudocode, because we didn't do it last time. And then we're going to do a couple of examples. We're going to run that pseudocode as we write it today on graphs, on concrete graphs. So let's start with that pseudocode. We're going to call it procedure, Dijkstra. And what's the input to this procedure again?
A graph and then a source node and
yes,
terminating node.
Okay, we could do it that way. Let's just simply take the source vertex and find the shortest path to everywhere else. So yes, let's take two inputs in this graph. The graph, this G, the set of vertices V and the set of edges E, is a weighted graph. And then we have a special vertex S. This S is going to be one of these V's that are a part of that are the vertices of G, and then we want to compute the shortest path from S to everywhere else in the graph. Now, as an aside, before I start writing down the pseudocode, how do you read a graph? So, I mean, I think I mentioned last time that it's a good exercise to write this algorithm in your favorite programming language. It doesn't really matter what the language is. Just simply translate your knowledge about Dijkstra's algorithm into any programming language and simply run it on a sample graph. I mean, I guess that's easier said than done, although the algorithm itself is not very complicated, right? There are a few side issues to contend with, right? For example, how do you read the graph? How do you represent the graph when you read it, and so on and so forth? There's quite a bit of details. It's not just that simple to just simply write it, right? But if you've taken programming 2 or something like that, the second class in programming or some data structures kind of class, how did you deal with these issues? So how do you read a graph? This is an aside, by the way, but let's talk about this for just 1 minute.
So we could, if we use an adjacency list, I know this is how we did it in data structures, but you can just get, like the degree of the source. So then we would just.
Okay, so you're only, okay, yeah, that's correct. I know you know it, but normally these graphs are stored in text files, right? So I think that's the way we did it in data structures, if I'm not mistaken. So for example, a weighted graph, we read like a bunch of lines of text, and each line was something like 1, 7, 17.5. The next line was maybe, I don't know, 2, 3, 22.5, 1, 3, 27.8, or something like that. So you had a bunch of lines. So each line had 3 entries. And what this meant is that the vertices were numbers in that representation. That's the easiest way to represent the graph, right? And then you can associate these numbers with anything else, whatever the vertices represent. Could be like, other textual information. But, let's say we have these vertices that are numbered, like 1, 2, 3, 4, like in this graph. Okay, 1, 2, 3, 4. And if you read an entry, something like 1, 5, 20 on a given line, it says vertex 1 is connected to vertex 5, and the weight of that edge, of that connection, is 20. So you read a graph like this, okay? You may have like a couple of extra helper lines, maybe you have a couple of lines that come before that say how many edges and how many vertices you have in the graph, but maybe not. Anyway, you read the information about the graph and you process it somehow with some helper code that builds the adjacency list representation of the graph, for example, or an adjacency matrix representation of a graph, whatever. But by the time you get to writing Dijkstra's algorithm, you have a way of reading text from a file and converting it into a data structure that is a graph, like an adjacency list that your Dijkstra's algorithm can recognize as a graph. So that's separate code. So you normally, as you go through your programming career, you write your own library functions like that. So like reading files, processing them, and so on. Or if you start working before you had a chance to create your own library, if you're like as a software developer or a software engineer somewhere, then the company will have these things, and you'll have to learn that like the way they do it. Anyway, that's a separate issue. Now back to our own concerns. So we have some way of reading this information into computer memory, and now we have to write down Dijkstra's algorithm in pseudocode that takes that information about the graph and outputs the shortest distance from the source vertex to everywhere else. So let's do that. Finally, we're getting to the point. I'll edit this video if need be to take this information out. So let me actually remove this. All right. So now remind me, how did we run Dijkstra last time? What did we do? We had what we called an initialization step, right, in Dijkstra. What this did is, okay, so we should probably write this down. So here I'm going to have d of s, d of v, let's say, notation, represents the distance from the source to this vertex v. Well, we're going to keep this notation, d of v, dist of v, whatever. Let's call it d of v, so I don't have to, too much to write. Okay, so the initialization step is take this vertex s and say that the shortest distance to that vertex s is 0. Okay, from source to source, I got in at 0 cost. Then you have this initialization step that assigns for each vertex, each v in the set of vertices. Well, actually, I should write down in the set. Yeah, in the set of vertices, v without s. So every other vertex. So take every other vertex that's there and assign the distance to that other vertex is going to be infinity. That's the initialization step. Then, if you remember last time, we had a couple of, so we had the set S that we call the cloud. What was that about? So far, this is just the initialization step. We took every vertex in the graph and assigned, and we're saying here that the distance to each vertex of this graph, except for the start vertex, is an infinity. That's our best estimate of the optimal distances to those vertices as of right now. So as we run Dijkstra's algorithm, we'll be changing our best guesses, our estimates, these infinities for now, to better estimates of the distances from the source to those vertices. That will be the point of Dijkstra, that once we are done with it, to every vertex, we're going to have an optimal best distance from the source to that vertex. And when do we say that we have an optimal distance to the vertex? We talked about last time. I know this is kind of a vague question if you don't remember exactly what happened last time, but we had this special cloud set S that we talked about. What was that about last time? So what was that cloud about? It was that big, we had this set S, okay?
You were weighing all of your options from the original source point to whichever vertices connected to it, and then you would go to the lesser value of the weighted.
Yes, so you're describing how we were adding these vertices to the set S, but what does it represent, this cloud, we call it cloud? The distances to the vertices that have already made it to the cloud, we're already declaring that those are optimal distances. So once the vertex makes it to the cloud, we're saying that we have an optimal distance to that vertex. So S will keep the set of vertices, which we are expanding at each step of Dijkstra's algorithm. So each step, which I haven't yet written down, we're going to have a little for loop here in a second, or a while loop, that adds a vertex at a time to this set S. And once we add a vertex to the set S, we're declaring that we know the shortest distance to that vertex from the source. So S, again, represents this cloud of vertices to which the shortest best distances are known from the source vertex. Does that make sense? Okay, so initially that set is empty. But then we add to it one vertex at a time, and we're drawing those vertices from from the set of vertices of the graph. Now we're going to keep those vertices in a special data structure that will, if you're familiar with priority queues, that's going to be a priority queue that's implemented as a min heap. But that's for us is irrelevant. So what we care about is every time we'll look at a set of vertices that are in the queue, we just want to draw the shortest, the best. Okay, so more detail on this. So let's talk about what that is. So we start with all these vertices V that are originally in the graph. This is that V. Okay, we'll put them, think of it as an array, if you will, but it's a priority queue if you're familiar with what that is. Otherwise, think of it as we store them in an array, all these distances to all these vertices for now. Now let me write the heart of the algorithm. which is quite short. Okay, so while this queue, the vertices that I'm processing, while it's still not empty, okay, so we start with the entire set of vertices Q and we'll be putting one at a time to the special set S. Once we've put every vertex from Q to S, the algorithm will complete, because of, the only way to put a vertex on S is to know the distance from the source, the optimal distance from the source to it. So inside the while loop, we're going to check, we're going to look at we're going to pick a vertex that's the best in this queue. Now, from what is that? So let me just first write this down. So we're going to say get the best. It's usually called extract min. It's a priority queue, so I'm going to write it that way. So I'm going to say the extract min element from this queue. Well, what does that correspond to? Just as a reminder from last time. Here's our example from last time. We looked at each row and we picked the smallest element, if you remember. So look at each row. These are the vertices that are on the queue. So right now on this queue, I have these 4 vertices when I'm at this line. So I look at these entries and I pick the smallest one. So I compare 10, 3, infinity, infinity, which one is the best? And pick the best one. So here, the best, by best, we mean the smallest entry. So we put that smallest entry, we take that smallest entry, and we put it on a special set S. We say that S now is augmented by we add another element to whatever S was before, put that vertex U on that S. That's it. That vertex U now we know the shortest distance to it. And now look at every neighbor of that vertex U. And as you've just described a few minutes ago, do some updates. Okay, what exactly? What kind of updates? So first, for each vertex, each V that is in the adjacency list of U, right? So when you read this graph here, you've constructed the adjacency list, this graph. So now it's assumed that we have an adjacency list representation of this graph. So you look at the adjacency list of this U. So everything that neighbors that vertex that you've just added to S, and you do the following. You check the distance. If the current distance to this vertex V that you've just extracted is bad, that if it is worse than a way of getting to this U, which you know to be optimal because U is on the set S, plus the edge cost of getting to V from this U, if that is better, then you update the distance to V. Then you say the distance to V better be this distance to U plus the edge cost. That's it. That's entire Dijkstra's algorithm.
I just have a quick question.
Yes.
So the distance, so like in the if statement, if distance to V is greater than distance to U plus the cost of like 2V from U, shouldn't we only update it if it's shorter than that, like less than the sum?
No, we should update it when it's greater, because if my current estimate to V is bad, right? If it's greater than this way of reaching.
Oh, right. Okay. Yes, I see.
Now, by the way, all of this will become very, very clear as we run it on an example. Right? This is called, by the way, the relaxation step, and it is a special case of an inequality that comes in mathematics every time, called the triangle inequality. Like everywhere you look in mathematics, you see some form of triangle inequality, and here it is in dynamic programming. Okay, when you take further classes, like it looks like we're not going to prove the correctness of Dijkstra, although we'll talk about why it's correct, but we're not going to do a strict proof of it. When you prove it in some like algorithms class that talks about dynamic programming and greedy algorithms, because that's where Dijkstra falls, shortest paths falls, then you talk more about this relaxation step. Okay, but anyway, all of this will become very, very clear now in a minute. This is, let me copy this. It's called procedure Dijkstra. I'm going to copy this. And I'm going to take this here. Paste this. And what we're going to do now is we're going to look at our pseudocode. Okay. And we're going to run the pseudocode on this particular example with your help. Okay, so let's get started. So first of all, what do we have in this table? This is the way you'll be filling out the table. You'll be answering the questions on Dijkstra, on the quizzes, on the midterm, on the final, whatever. So you'll normally have like a graph like this given, and you'll be asked to fill out the table exactly as I'm about to do now. The point of this is that you're running Dijkstra's algorithm. Obviously, you can't really bring a large graph on the test. So each one of you can just simply look at the graph and tell what the shortest distance is from one point to another. So that's not the point. That doesn't answer the question about Dijkstra. The question about Dijkstra is to run the algorithm itself, that is to fill out the table the way we'll be filling out this table now. The point is that every entry in the table should be exactly as Dijkstra tells us. That will be part one of the question that you'll see on the quiz. Part two of the question would be to draw a spanning tree, a shortest distance spanning tree for the graph. What's a spanning tree of a graph?
I think it's, sorry about that.
Yeah,
Go
please.
ahead.
It's just like the shortest way to get to any node pretty much at once the algorithm is done.
Yes, it gives that information, but the table also gives the information. Okay, spanning tree. Okay, we'll talk about this after we run this, but so first of all, what is a tree? So let's since we brought this up, let's just say what a spanning tree is and move on. So what's a tree, first of all? What's a tree? Somebody has the definition in their mind? What is a tree?
A connected graph with no cycles.
A connected graph on no cycles. A tree is set to span a certain graph, like this graph. Let's take this graph. If the vertices of the tree are exactly the same as the vertices of this graph. So what we want is a tree with the same vertices as this guy. But now this time that it will be a tree, not just a graph like this that may have cycles here somewhere. How many edges will a tree have if it has n? Looks like n is 8 here. Looks like we have 8 vertices. How many edges will that tree have? So that's one definition of a tree, the one that you gave us. It's a connected graph with no cycles. But suppose a tree has n vertices. How many edges will it have?
n-1.
Yeah, it has one fewer edge, right? Okay. If you added one edge to that, you'd close a cycle. You'd have a cycle. So you want the tree to be a connected graph with no cycles. Anyway, I'll return to this in a minute. First, let's run Dijkstra. Again, the point of this was that there is a part B to the question on Dijkstra in the quiz. Will be, show me the tree, the shortest path tree, that will be a shortest path spanning tree on this graph. And the point we're trying to make here is that running Dijkstra gives the information needed to construct that spanning tree in a second to draw it. So to draw that spanning tree, all we have to do is to look at this table that we're about to fill in. And we'll fill in this table by running this pseudocode. So now with your help, we're going to start filling in this table. Okay, so I'm calling procedure Dijkstra. I gave it the graph. So this somehow we know how to read the graph and construct an adjacency list representation of that graph, which is what we're using here. Okay. So what's the first thing it says? So by the way, on the right side here, this is our special set S. We'll be putting the vertices there on that special set S. Okay, that's our S. Big S. Okay, so what's the first thing that it does? So help me out, please. And we're going to have to do it with your help, especially if you don't have the webcam on, right? So please help everyone out so that. All right. So what am I doing here?
Well, I'm just like confused, like which vertex is S, like in the call?
Oh, yeah, there it is.
Oh,
yes,
not it.
the start vertex. Okay, so yeah, start. This is the start. S,
right.
Small s. So we'll start here. Good point. Okay, so we start there. So what do we do?
So in the table, S would be 0, right? And then for each one after that, it's infinity.
Okay. So we just ran this initial, this is called the initialization step here. This is the initialization step. So S is initialized to an empty set. There's nothing on S at all. As we add vertices to S, we'll be putting those vertices here, the vertices that go in S. And what's on Q for now? All of these vertices are on that Q. All these vertices are there. Okay, that's great. So now I've done the initialization step. I got into this while. Okay, so I have to execute this while because I have stuff on the queue. It's not empty. Okay, well, I'm going to have all these vertices in that queue. Okay, so now I'm going to extract min from the queue. So I look into my array. So think of, if you don't know about heaps and priority queues, all that stuff, and you don't have to, who cares? Think of it as an array which stores these entries. And simply extract min. The reason we say priority queue here is just we want this extract min operation to be fast. But if you don't care about it being fast for a small example like this, think of it as searching an array and getting the smallest element out of the array. That's all. So what's the smallest element in this array?
0.
0. Okay, so I extract 0 from here, extract min, and put it on my special set S. Let's make that set blue. So I'll have to be switching here between colors. Okay, so I put that 0 vertex on that S. So here I am in this run of this algorithm. I just ran this line, just got the smallest element and put it on my special set S. Now on my set S, which was originally empty, I have this one vertex right here. Now I'm inside this for each loop, which is inside while. So I look at every, okay, so what do I have? So my U is 0. What's my adjacency list of U?
1, 4, and 7.
1, 4, and 7. So I'm looking, this is red, right? So 1, 4, and 7. This is 1, 4, and 7. So here they are, 1, 7, and 4. These three guys are in the adjacency list of vertex 0. Okay, so what does this algorithm tell me? So now I'm with your help. I'm just reading, I'm playing a role of a computer. So receiving an instruction from you. So what should I do? I'm checking the distance. What's this distance to V right now? What is V? What is V? Okay, so we agreed the U is 0. What is V here? I'm inside this for each loop. What's V right now?
1.
Maybe trick question. Yes, it doesn't really matter which one you process first. It's a set here. Doesn't really. So pick 1. Okay, let's pick 1 since you've suggested 1. So let's start with 1. What's the distance? What's the D of V right now?
Infinity.
Infinity. It's infinity right now, right? So D of 1 is infinity. Some people like to annotate this graph. So let me actually do this, although this is extra work, but all the information that we need is right here. So some people put these infinities here and the vertices, and once they update this distance to 1, they put a 5 up there. You can do that if that helps it. But you can also write this, but you should also write this information inside it. So I update this infinity with 0 plus 5. Does that make sense? I compare this infinity to 0 plus 5. And because 0 plus 5 is smaller than infinity, I do this, I execute this then clause here of this if statement. The then clause gets executed and it replaces this infinity by a 5. And I also mark it the predecessor where I came there from. So I mark that I got there from 0. Okay, then I look what else is on the adjacency list. The next one, let's say it's 4. So what should I do with 4? What am I doing? So help me out. So which line am I on?
On the if statement, if
Yes.
The distance to 4 is greater than the distance to U plus the cost of U to from 0 to 4.
Yes, and what's the cost from 0 to 4? 9, right? 0 plus 9, the total cost. So infinity is larger, so I replace that with a 9 and say that I got there from 0. What's the distance to 7? Well, currently you say it's infinity, right? But the way of getting, now I have a new way of getting to V that I can change this estimate to a better estimate. The distance to V is no longer infinity, but rather it's 0 plus 8. So I write down an 8 here. Okay, an 8 here. And I say that I got there from 0. Everything else I just copy over. Okay, there's no way for me to reach 3. So as far as I know, the best way of reaching 3 is still infinity. I can't reach 2 at this stage, or 5 or 6. So I copy those over. So now I'm done with this for each loop. There's nothing else here, no other statement. So now I get back to while condition. Is my queue empty? Well, no. What's on that queue? 1, 2, 3, 4, 5, 6, 7. All these guys are on there. The only thing that was popped off of it was this vertex 0. So I still have a few things to do inside the while loop. So what's the first thing I do? Now I'm at that. So I continue executing this while. First thing, This is exactly what we did last time, but now we're just following the pseudocode. So what do I look at this? Well, think of it as an array if you'd like, or a heap, whatever. But I look at this and I do what?
Select the smallest value and add it to S.
Yeah, exactly. I pick the smallest value, and the smallest value happens to be what? 5. And what do I add to S?
1, the node 1.
The node 1 goes to S. So I'm at this line here. I've just added this 1 to S. Okay, so I had a 0 on that S. Now I have 0 and 1 on this S right here. What do I do next? I look at what? So let me make sure. So now my U is going to be 1, right? So we're looking at 1, we're processing now. What's the adjacency list of 1? What's the adjacency list of 1?
2, 3, and 7.
Yeah, these 3 guys are on the adjacency list of 1, nothing new. Notice that a way of getting to 3 was infinity. Now I have a new way of getting, I have a way to reassess my estimate of a way of getting to 3 from infinity to something better. Why? Because, so we're processing this vertex 3. Way of reaching 1 is what?
5.
5. What is the edge cost of getting to 3?
15.
15. Is this better or worse than my current estimate to 3, which is infinity? So, well, infinity is worse, right? So I update this. What should I put here?
Should be 20 coming from 1.
20 coming from 1. That's exactly right. All right, so what's the way of getting to 2? And by the way, people do this. You update this to 20. You update this to 8. You update this to 9. Was in the previous step. We've updated 3 to 20. Okay, now what do we do with 2? I compare this infinity to what?
You could also pull that one from 1 and do the 5 plus 12. We want to get the 2 from 1.
Yes, so 5 plus 12, right. So now the estimate is what, 17, right? Because it's better than infinity, and you got there from 1. What else do I do here?
I think we would then examine the edge to 7, but it's not less than the current weight, so we don't
Yes,
update.
yes, but let's that you're absolutely correct. You're absolutely correct. So let's just we have to examine it. So we're just now we're playing the computer. We're not doing that much thinking, right? So we're just following this. Just let's follow this through. The way of getting to 7 currently is 8. 5 plus 4. Okay, is this better than 8? That's the question. Well, it's not. You told us 9 is worse. So we copy this 8 over. We're not making any update to it. And we copy this over. So we're not changing. Is there a new way of reaching 4 at this stage as we're considering vertex 1? There's no edge to 4. So we copy 4 over. Notice one thing. As a human being, which we're not trying to be here, we're trying to be a computer. As a human being, you know for sure that the best way of reaching 4 has got to be just at the cost of 9. But the algorithm doesn't know that. And why do you know that as a human being? Because there's no other edge leading to 4. The only edge leading to 4 is from the source vertex to 4. And that's it. There's no other way of reaching it. So it's going to be a 9, but the algorithm doesn't know any of this. Why does it not know? Because vertex 4 has not made it to the special set S. Once it makes it to the special set S, you as a human being can predict that it's going to be at the cost of 9. But the algorithm doesn't see that at this stage. It doesn't know what the best way of reaching vertex 4 is. So we're just following the pseudocode. Okay, so no way of reaching 4, so I just copied this 9 over. It's not optimal yet. Soon I'll know that that's the optimal way. As of right now, I don't. I still have no way of reaching 5, so I copy that over, and I have no way of reaching 6, so I copy that over. All right. Okay, so I've just reached this line. So I'm going back up to while, back up to while. And I still have stuff to do because I have all these vertices that are still on my queue. I've only added like 2 out of those vertices to S. So I look, now I'm at this line. So I have to find the smallest element, it says, in this array of entries. Okay, I may have some efficient data structure in the back that allows me to find the smallest entry, whatever it is. And so it does its job and tells me that the best entry here is going to be 7. So the next vertex that goes onto S is going to be 7. Make sense to people? So 7. And now what this tells me is that my current U is 7. Okay, this is my current U. And what's on the adjacency list of 7? Well, there is a 2, there is a 5, and that's it. There's only a 2 and a 5. There's nothing else on it. All right, so let's examine them one at a time. What's my best way of getting to 2 right now? So what's my V? We're starting at 2. What do I have distance to V? What is that?
17.
17. Is it better than, what's here on this side? What's the distance to U?
8 plus
8
7.
plus 7. Okay, so is 8 plus 7 better than 17? Is it?
Yeah.
Yeah, so I update my entry of 17 to the better entry. Now I say it's 15. The best way of reaching 2, as far as I know right now, may not be optimal yet. I haven't put that vertex in the special set S yet. But as far as I know, the best way of reaching 2, my best estimate is at the cost of 15, and that's through 7. Okay. What happens to 3? Do I have a new estimate to 3? No, I don't. I copy that one over. Do I have a new way of reaching 4? No, I copy that one over. New way of reaching 5? Yes, that's on my adjacency list. So now I'm looking at the next V on my adjacency list of U. What's my estimate to V? Infinity. Is infinity greater than the distance to U, which is 8, plus the edge cost to 5, which is 6. So it turns out that 8 plus 6, so I think about it for a while and I determined that 8 plus 6 is probably better than infinity. So I replace that infinity with my new estimate of 14, getting there through 7. I still have no way of reaching 6, so I copy that infinity over. And that's it. So I'm done. I'm done here. Make sense? So now I go back up to while. What's on my queue right now? Every vertex other than what's on S. That is all these vertices. Q and S are complements of one another in the set of vertices V. So I've popped up only these vertices from Q. I'm still left with these guys to process. All right, so now I pick the smallest element. So I'm at this line. So extract min. What's the smallest element here? So I think about this for a while and decide that 4 is the next guy to go onto S. That's the smallest one. So I circle that and put it on my special set S. And now I look at everything that 4 is adjacent to. Okay, so 4 is my next new U here. New U here is 4. So what's on the adjacency list of 4? So help me out at this step. What's on the adjacency? So this is the time that 4 has made it to our list. What's the new stuff that goes out to 4?
7, 5, and 6.
7, 5, and 6. 7, 5, and 6. Now, do I have to look at 7? 7.
No.
Yeah, 7 is already on my special set S. I'm declaring and we haven't proved correctness of Dijkstra, but if Dijkstra is correct, the distance to 7, the vertex 7, should now already be optimal. the fact that we have a new way of reaching 7 somehow through 4 shouldn't matter. This new way should be worse than we already have. That's a good check. Like, it's a good check to perform. What's our best way of reaching 7? It's 8. A new way is 9 plus 5, which is twice worse. Okay, almost, of getting to 7, which is worse. What should I say? I should say this is worse than that what we already have, and that better be the case. Otherwise, Dijkstra wouldn't work, wouldn't be correct. Because if I put something on S, then I'm declaring that I know the shortest distance to it. And if something new now gives a better estimate, that means my algorithm is incorrect. Okay, the claim we made about the algorithm that everything on S is already optimal would be incorrect. So anyway, so we don't have to check this 7 because it's already put on the list S. Okay, so but double checking it, it works out. The new way is 9 plus 5, which is 14, and that's worse than 8, which is what we already have. Okay, but then I have 2 other edges emanating from 4. There's this 5 and this 6 here that I can reach from 4. Okay, so let's start with 5. What's my best estimate of getting to 5 right now?
14.
14. Is it better than 9 plus 4?
No, it's not better.
Well,
Like,
it's not.
14 is not better.
Yeah, 14 is not better. So now, and this goes back to your original question, right? So which one is it? This way, inequality, or so? So it is this way because 14 is worse. Then I do this update. Then I have this clause. So I update my 14 to 13 now. So here's my update to 13, and that I got from 4. What's my estimate to 6? Well, it was infinity. I haven't even seen this vertex before, but now I'm beginning to look at it from my cloud S. Okay, and my perch in the cloud is vertex 4, from which I see 6. And the estimate to 6, instead of infinity here, which is worse than 9 plus 20, right? The cost of this edge is 20. So I replace this infinity here with what?
29.
29, and I say that I got there from 4. This guy 3 hasn't been updated, and that's it. I'm done with my adjacency list. Now I have to copy over everything else. Okay, so 2, that copies over. 3 I haven't seen for a while, so I copy that guy over. I haven't looked at 3 in a while. Okay, so I'm done with this for each. I'm done with while. So I go back up to the top of while. My queue is not empty. I still have 4 elements in it. So I pick the smallest one of these 4. What's the smallest one? Five comes off this time, right? Am I correct? 5 comes off. And what's on the adjacency list of 5?
2 and 6.
It's 2 and 6. It's the only 2 vertices on the adjacency list of 5 right now. So I process them one at a time. Let's look at 2. What's my best way of reaching 2 right now? I've updated it once before from 17 down to 15. I revised that estimate, but now I have what way? And by the way, I haven't updated these. So let's just, you can do the updates here in the graph as well. I'm going to erase it because that's just extra needless work, given that we're using this table, but you can use those updates on the vertices directly on the graph if that makes you, if you think that's easier. Okay, so what's my way of reaching vertex 2?
It's currently 15.
It's currently 15, but from 5, it's going to be what?
14. 13 plus 1.
Yes.
Yeah.
So I have a better way of reaching that vertex. So I put a 14 there of getting to 2. And I got there from 5. How about reaching, what's the next? So help me out. So what am I doing here? Just process this. What's my next step? What am I doing? So somebody who doesn't have the webcam on help me out? I'm stuck. What's my next step? Somebody who doesn't have a webcam, do we know where we are in this algorithm, or there are
You
like
just put 2 in, so next step is 6, right?
yes, it's exactly okay. So glad to know that someone without webcam is here. That's important. 6, the best way of reaching 6 before was 29. right? But now the best way of reaching 6 is, instead of 29, it is 13 plus 30. So what was your answer? So what should I do here? What am I comparing to what? Like anyone know? 29 comparing to what?
26.
To 26. So I have 26, and I got there from 5. This poor guy 3, I haven't seen in a while. I have to copy that entry here. I got there from 9, and that's it, right? There's nothing new. Okay, so now I've reached this. Going back up, I still have these 3 vertices here in my queue, so I pick the smallest one. What's the smallest one now?
2.
Yes, it's vertex number 2. So I take it off, and this is the line that I'm at. I've added my 2 to my S right here. And I look at the adjacency list of 2. So I'm back down, back at this adjacent, at this line, at this line, at this line. So I look at the adjacency list of 2. The adjacency list of 2 has 2 vertices. It has degree 2, vertex 3 and vertex 6. What's the way of reaching vertex 6? Right now.
Currently 26.
26.
From 5.
Is it better from? Is it better than 14 plus? So 11, right? It turns out, as you've just told me, that's 25, and 25 is better, right, than 26. So I update this 26 with a 25 here. So now this 26 has just become 25, and I got there from 2. That's an update. What else do I have to do here? I've just updated this 6. I have to look at the other guy that's on my adjacency list. That's 3. My current estimate of getting to 3 is 20 units. My new estimate of getting to 3 is what?
17.
Is now 17. Is exactly 17. It's now 15. Oh, is it? Yeah, 14 plus 3. So now it's 17. And that's from vertex 2. Okay, that's it. There's nothing else. Everything else, I'm done. I got here. I come back up, check if there's still something left on my queue. And yes, I have 2 elements left. This guy and that guy. So I have to process those. So I pick the smallest element. What's the smallest element in my queue? So help me out. What do I put here? Somebody. What goes?
3.
3 goes there. 3 goes there. And my adjacency list for 3 is what?
6.
Is only guy 6. There's only one element in that set in the adjacency list of 3, 6. And what's my current estimate to 6?
Currently 25.
Currently 25. Is it better than getting to 2 at the cost of, to 3 at the cost of 17? So I have a 25 here. The cost of 17 plus what?
9.
9. So is it better?
No.
No, it's bigger than 25. So I leave my 25 alone. I just copy it over. And I know that the best way of getting there is from 2. Again, I've reached this line. Go back to while. Is there still something left on the queue? Yes, there's one guy. So I take my sweet time to find the smallest element in this queue of one element. And it turns out to be just 25. So I extract that. And I put, finally, 6 has made it to this list. 6 is here. Okay. And now what's next? What do I do next? Okay, on the quiz, you stop here, obviously. Don't waste any more time. But here we're following the pseudocode. So I just put this here. Now I look at what?
You look at the adjacency list for 6.
You look at the adjacency list for 6. And what's on it?
Nothing.
Nothing. So I have nothing to process here. Okay, my has nothing here. Comes back right up to while. Checks what's on the queue. Now it's empty. So it jumps right down here to this line and exits the procedure, whoever called this procedure. Okay, and then does whatever else needs to be done. Maybe you want to print something or whatever else. Okay. So that was the run of Dijkstra, right? That was the run of Dijkstra. Now, this is just part A of the question. Okay. What's the second piece? Now the claim is that from this table, we can reconstruct the shortest path tree. The shortest path tree will be a tree and the same set of vertices as the original graph. So let me just copy all these vertices here. So I have the same 8 vertices that I had before. So I'm building a tree on this graph. So these are the same vertices, same graph. And now I'm going to build a tree here by looking at my table. And again, each row on this table, in this table, will correspond to an edge that I'm about to add to this spanning tree that I'm drawing right now on these vertices here. The spanning tree will go here. And from each row, I'm going to extract an edge. How? Let's just pick any row that makes you happy. Let's go with 2. So here's 2. This is the point in the table, in the run of Dijkstra's, where I put 2 on my special set S in this row. Well, this row tells me that the cost of reaching 2, after all this work up here before, the cost of reaching 2 was 14. So I annotate this 2 with a 14 here. And this same table, same entry, also tells me that I got there from 5. So I go ahead and draw an edge here from 5 to 2. From 5 to 2. This edge is part of the spanning tree. It's part of the spanning tree of this graph, shortest path spanning tree of the graph. Okay, so let's pick it, and now you help me draw the next edge. Just first, let's pick, I don't know, what should we pick? Let's pick 3. When did we add 3? We added it right here. How did we get, okay, so let's pick 3, fine. Could have picked 7, but fine. Since we picked 3, we got there from 2, right? So we got there from 2, and the cost was 17 to get to 3. Okay, let's pick, let's pick 7. So help me out. How did I get to 7?
We got there from 0.
From 0.
At the cost of 8.
At the cost of 8. So I annotate this with an 8. How good did I get to 5?
From 4.
From 4. So I draw this edge from 4. Notice that I'm adding one edge at a time as I'm considering each vertex. Each row corresponds to a vertex. And every time I look at a vertex, I add an edge, except for this case, like the source vertex. So how many edges do I add to this graph? So each row is a vertex. Sorry?
I was going to say 7.
Yeah, n minus 1.
minus,
One
yeah.
fewer, right? One fewer. Because I don't add an edge for the source vertex. For every other vertex, I add one edge. So the number of edges I'm going to have is going to be n minus 1 at the end of the day. Okay, so let's look. How did I get to like 6?
From 2.
From 2. So let's add this edge there. And what's the cost of reaching 6?
25.
25. So I got there at the cost of 25. Okay, got to 2 at the cost of 25. How did I get to 4?
From 0.
From 0 at the cost of 9. And of course, you knew this the very first second you started this algorithm, right? But the algorithm found this out at some like midway here. Okay, so we add this now to our edges, and that happened at the cost of 9. Finally, how did I get to 1?
From 0.
From 0 at the cost of
5.
5. That's what the table told me. So I extracted all this information from the table. And now I'm left with a structure that looks just like that. Is this a tree? As you've just told me, I added n minus 1 edges to it. Is it connected? Does it have any cycles?
No.
And as n minus 1, there's no room for it to, not enough edges to make a cycle. N minus 1 edges. Okay, so that's what's called a spanning tree. Why is it called spanning? Because it includes all the vertices of the original graph. It spans the original graph. Why is it a tree? Because it has n vertices and n minus 1 edges. It's connected graph. And it has no cycles. It's a tree, and it's a spanning tree. Makes sense, right? That's what Dijkstra gave us. That's the output of Dijkstra. Now, we took quite a bit of time to do this. Now, this time, then let's do one more, but this time, let's do it at a speed that you will do it on the quiz after practice. Okay? So let's take this other example. Oh, let's, what is this? Okay, yeah. So let's take this example here. Let me paste pseudocode just in case. But now let's do it a little bit quicker. So help me out. What's happening here? This is my original graph. My source vertex is is 1, let's say. So I initialize. So I run this in the init. This is called the init phase. Initialization phase, this one. And now I get to the while loop. Okay, let's take a look. Initialization step right there. First line, 0 to 1, the distance of 0 to 1, and infinity everybody else. What do I do next? So let's do this quickly. We have like 5 minutes left. Let's do it in 2 minutes. I look at everything emanating from 1. I have 2, 3. This time, let me annotate the graph too, because some people like doing this on a graph. So initially, these were my estimates, these infinities. I'm doing some extra work this time. I remove this infinity and put a 15 there on the first step. Remove this infinity, put a 35 there. Remove this infinity, put a 20 there. This is what's happening here in this table. Everything else is still infinity. That's this row. Now I'm at this line. Get the smallest element out. What's the smallest? I look into this row very carefully and find this to be the smallest. So I get this guy out, which is 2, and put it in my special set S. Now I'm looking at everything that's emanating from 2. I have this edge, and I have this edge back to 1. Do I consider this edge back to 1? No, I don't have to consider it because 1 is already on my special set S. I know the shortest distance to it to be 0 already as an algorithm. So I look at this edge at the cost of 40, and I find that infinity is larger than 15 plus 40. So I put a 55 here, and I say that I got there from 2. Put a 55 here. Then I have no more edges. Oh, okay, so yeah, no more edges emanating from 2. So what do I do next? Well, first of all, I copy the other guys, this 20. I copy these infinities. I copy this 35. What do I do next?
Pick the smallest one.
Pick the smallest one. The smallest one is going to be this guy. So I circle this guy, and that's vertex number 5. So I look at everyone that's emanating from 5. 3 is one of those vertices. Well, do I consider 1? 1 is also a vertex that I can reach from 5. This is an undirected graph. Do I care about 1? No, because it's already here. I can reach 3. I have some estimate to 3, but this is, I don't know if it's the best. So I have, it's not yet on my set S. So I look at this edge. It's the cost of 10. So help me out. What do I do? Do I erase this 35 and put 30 there?
Yes.
Yes.
Okay, so I got there from 5. Do I erase this infinity at 6 that I have and put a 70 there?
Yep.
70. I got there from 5. Do I erase this infinity at 7 and put 95 there?
Yes.
Okay. Do I do anything with this entry for 4? There's no new way of reaching 4, so I copy that entry over.
Okay.
Right. So now what's happening now?
Look for the smallest one.
Look for the smallest one. So what's the smallest one?
3.
It's 3. So I add that 3 there. So now I'm looking at everything that's emanating from 3. I can reach 5, but 5 is already on my set S. So I don't care about this reaching 5. I can reach 4. So I should care about that. I shouldn't care about either 1 or 5, but I should care about 4 because it's not yet on my set. What's the best way of reaching 4? 55, right? What's the new way of reaching 4?
65.
65. Do I update anything?
No.
No. So I copy all this. And notice at this step, there's no update being done. So I just copy this 55. I just copy that 70. I just copy this 95. And again, I look at the smallest entry. Now the smallest entry is 4. So finally, I decide that the best way to get to 4 is at the cost of 55. And I look at everything that emanates from 4. Do I care about 3? Do I care about this edge? No, because 3 is already there. Do I care about this edge?
Yes.
Yep.
Yes, I care about this edge. Because although my estimate to 6 is 95, oh no, it's not 95. What is my estimate to 6? 70. My estimate to 6 is 70. This new estimate may be better, maybe not. I don't know. So let's check. So this 10. Oh, I'm sorry. Where am I getting? What am I talking about? Yeah.
4. Yeah, 4.
Yeah, 4. So 10. Okay, 55 plus 10. That's 65. So it turns out that it's a little better than what I had before. So I say that I got there instead of at the cost of 70 from 5. I got there at the cost of 65 from 4. Okay. Do I do anything with 7? Vertex 7?
No.
No. Okay, so that's it. There's nothing else. Okay. So I have 2 entries left in this row. So what do I do here?
Take the smallest.
Pick the smallest. What's the smallest?
6.
6. So I put 6 on the special set S, and I look at what's emanating from 6. The only thing I care about, although I have these edges back to 5 and 4, those are already on the special set S. So I know the shortest distances to those vertices. So I don't care about these 2 edges, but I care about this edge. My best way to reach 7 is at the cost of 95. But now, what's the best way to reach 7?
85.
Yeah, it's 70 plus 15, exactly 85. So now it turns out that the best way to reach 7 is at 85. Then I look at every entry in this row, of which I have just 1, and I pick the smallest. That corresponds to vertex 7. So I put that vertex 7 onto my special set S. Okay, so that's it. Now look, 85. Then I come back to this line. Looks like my queue is empty. There's nothing left here. So I'm done. Exit, exit. Okay, great. So this is the run of Dijkstra. Now that was part A of Dijkstra's question. What's part B? Construct the minimum spanning tree. So help me out with that piece. So where's the spanning tree? So here's my source vertex. How did I get to vertex number? I don't know. Let's start. I don't know. Let's start with 6. How did I get to 6?
From 4.
From 4. So apparently this edge is there. How did I get? Oh, I should have updated this to 85. Okay, so how did I get to vertex number 3?
From 5.
From 5. So apparently this edge is there. How did I get to vertex number 4?
From 2.
From 2. How did I know? Because you told me. I also could have looked at this table. So this is when I added 4, and I got there from vertex 2 at the cost of 55. Okay. How did I get to 7?
From 6.
I got there from 6. How do I know? Because you told me, quite frankly, but I could have looked at the table. How did I get to 3?
From 5.
From 5. How did I get to 5?
From 1.
From 1. Okay. And finally, I should consider how did I get to 2, so that to make this graph connected.
From 1.
From 1. And that's it. I've just added 7 minus 1 edges. Those 7 minus 1 edges on a graph on 7 vertices with no cycles connected, no cycle, make it a tree. This is a tree. This is the spanning tree. This is the spanning tree. Spanning tree. Okay, so that's the answer to Dijkstra's. Is it clear what Dijkstra's does? So what we really expect is like everyone to ace this question on Dijkstra. Like nobody should lose any points on Dijkstra at all. So please do a couple of examples. Now the homework is a little easier. So don't be tempted to just simply look at those questions on the homework and, okay, I see the shortest path, and just, that's it, write down the answer and just move on. So you really have to, on the quiz, fill out a table like this and draw a graph, a spanning tree like this, shown in pink here, or purple, whatever that color is.